Welcome to the deep dive. Today, we're really jumping into something fascinating, the world of intelligent agents. These aren't just your average chatbots. We're talking about systems powered by large language models, LLMs, that could, well, potentially change quite a lot.
That's right. They could revolutionize things across many fields.
Absolutely. And our mission today is to unpack a big new research paper that gives a really comprehensive look at these agents. What makes them work, how they learn, how they might work together.
And crucially, how we make sure they're safe and, well, helpful.
Exactly. So the paper itself, it takes this brain-inspired approach, which I found quite interesting.
Yeah, it does. It tries to map the agent's functions onto sort of analogous parts of the human brain. It's a framework, really, to understand how you might build something intelligent by looking at, well, the intelligence we know best, ours.
It definitely helps make sense of it. Thinking about cognition, memory, perception, seeing how those pieces might fit together in an AI.
Precisely. And the paper starts right there with those core components, cognitive, perceptual, operational modules, mapping them to brain functions. It's like understanding an engine by looking at its parts first.
Okay, so let's start with that cognitive part, the thinking. The paper breaks it down into learning and reasoning, right? And for learning in LLMs, it seems like there are different levels. There's the big pre-training.
Right, where it just absorbs massive amounts of text data, general
It's
knowledge.
reading the entire internet almost. Then there's fine-tuning.
Yeah, that's more specific training. Supervised learning, reinforcement learning, making it better at particular tasks.
And then this in-context learning thing. That sounds like they can adapt on the fly, just from the conversation or text around them, without actually changing the model.
Exactly. It's quite remarkable. They can pick up patterns and instructions from the immediate context. But the paper also points out a key difference between this kind of data-driven learning and human learning.
How?
Well, we learn through exploration, curiosity, emotions play a role. LLMs fundamentally learn from the data they're fed. Researchers are definitely looking into how to make agent learning more, well, human-like in that exploratory sense.
And that makes sense. And tied into learning is alignment. Making sure these agents actually do what we want them to do, aligning with our values.
Crucial, yeah. The paper talks about techniques like RLHF, that's reinforcement learning from human feedback.
Okay. And DPO, direct preference optimization.
Right. Both are ways to use human judgments to guide the AI. RLHF uses feedback to train a reward model, while DPO learns directly from comparisons, which can be a bit more direct. It's all about steering them towards helpful, honest, and harmless outputs.
So for you listening, this alignment piece is super important. It's not just about making them smart, but making them, well, trustworthy.
Absolutely essential. And reinforcement learning pops up again when we talk about reasoning specifically, improving how they think through problems.
Like the mentions of RAFFT reinforcement fine-tuning and models like DeepSeek R1 or Kimi K1.5. Sounds like they're pushing how well agents can strategize.
They are. It's about teaching them the process of reasoning, not just the answer. Like showing your work in math, learning the steps.
That's a good analogy. Okay, so they need to think, but they also need to perceive the world, right? Take in information.
Exactly, perception. And that's becoming increasingly multimodal.
Multimodal meaning, not just text.
Right. Text, images, audio, potentially even touch down the line, integrating different senses, just like we do.
So models like CLIP, connecting text and images, or LVA for visual Q&A.
Cog VLM, Quinn audio for sound.
Yeah.
They're learning to process and connect different kinds of information, and retrieval mechanisms play a role here too.
Like RAG, retrieval augmented generation.
It's like giving the agent a library. It can consult in real time to improve its understanding or answer questions more accurately based on external knowledge, enhancing perception with retrieved facts.
Okay. Then within reasoning itself, the paper talks about structured versus unstructured reasoning. Structured sounds like laying out the steps clearly.
Pretty much. Think chain of thought, cohe, where the model explains its reasoning step by step. Or tree of thoughts, toti, exploring multiple paths. It makes the process transparent.
Like showing your work again.
Yeah.
Makes it easier to follow and potentially more reliable for complex stuff.
Exactly. And interestingly, just showing the model a few examples of structured reasoning, like with COTE, can encourage it to adopt that style. They call this long COTE and short COTE teaching reasoning structures.
And then unstructured reasoning is more intuitive. The model just gives an answer.
Kind of, yeah. It relies more on the patterns and knowledge baked into the LLM from its training. It can be faster, but less interpretable, like someone just knowing the answer.
Got it. The paper also mentions cognitive maps. like the agent building an internal representation of its environment.
Yeah, like a mental model or map. Especially useful for navigating complex environments like the web and anticipating what might happen next. They can function as world models in that sense.
And crucial for reasoning is factual accuracy, avoiding those AI hallucinations.
Definitely. The paper mentions methods like Refiner, which helps structure information better for the LLM, and chain of verification or COVE.
Oh, sounds like fact-checking.
It is, essentially. The model generates an answer, then it generates questions to verify the facts in that answer, answers them, and then gives a final verified response, a sort of self-correction loop.
Okay, that covers the thinking part. What about memory? The paper uses a hierarchy, right? Sensory, short-term, long-term.
Yes, drawing parallels with human memory. Sensory is the immediate input. Short-term or working memory is for the task at hand, and long-term is for storing knowledge over time.
And it maps these on to different AI systems or concepts.
It does. It talks about how agents might encode perceptions, sensory, use context windows, short-term, and build up knowledge bases, long-term. It's a useful way to structure how AI manages information.
And it's not just storage, is it? It's a whole life cycle. Acquiring information, consolidating it, and coding it.
Even deriving new insights through reflection or summarization. It's an active process. Things like compressing information, using attention to decide what's important, fusing data from different modalities.
Like combining text and image info in memory.
Exactly. And then processes like reflection allow the agent to learn from past experiences, not just store them.
But there are challenges here too, right? Balancing capacity and stability, making sure it can retrieve things efficiently.
Big challenges. How much can it remember without losing old stuff? How does it find the right memory quickly? And how does memory actually help it reason better? They mention ideas like associative memory, linking related concepts, or even integrating memory into the model's parameters.
Which leads nicely to world models. These sound like the agent's internal simulation of reality.
That's a great way to put it. It's the agent's understanding of how the environment works, used for prediction, planning, reasoning about consequences, like our own mental models that help us anticipate things.
And there are different ways AI builds these. Implicit, explicit, simulator-based.
Yeah, implicit models often use neural networks, powerful but sometimes hard to interpret. Explicit models define rules more directly, more transparent. Simulator-based ones use external simulations for training, but those sims might not capture everything about the real world.
And there's a trade-off between how complex the model is and how well it predicts things.
Definitely. And implicit models can sometimes overfit to the data they were trained on. Simulators are useful but computationally expensive and might lack real-world nuances.
And memory feeds into these world models, presumably.
Absolutely critical link. Past experiences and knowledge stored in memory inform the world model's predictions. And the world model helps interpret new experiences to be stored in memory. It's a feedback loop.
Okay. Next up, reward. Motivating the agent. The paper looks at the human brain's reward system first. Dopamine and all that.
It does, yeah, to understand the principles. But it contrasts human rewards, often intrinsic, complex, biological, with typical AI rewards, which are usually external, task-specific, and explicitly defined by designers.
And capturing human values in a reward function is hard.
Very hard. Nuance is difficult. So AI uses external rewards, like points for winning a game, but also intrinsic rewards.
Intrinsic, like the agent rewarding itself.
In a sense, curiosity-driven reward encourages exploring novel situations. Information gain reward encourages actions that reduce uncertainty that lead to learning. These help when external feedback is rare.
But designing rewards is tricky. Sparsity not getting feedback often. Misspecification rewarding the wrong thing accidentally.
Right. And generalization, a reward that works in one place, might fail elsewhere. Potential solutions involve things like learning rewards from examples or hierarchical rewards for complex tasks.
Fascinating. Then the paper touches on emotion-like systems, giving agents feelings.
Well, maybe not feelings like ours, but internal states analogous to emotions. Based on psychological theories, categorical, dimensional, appraisal-based models. The idea is it might lead to more coherent, predictable, maybe even understandable agent behavior.
So an agent might have a consistent mood that affects its decisions.
That's the kind of potential outcome being explored. Using emotion theories could make agents more interpretable and maybe better at social interactions. It's still early days, though.
Okay. Then perception systems, how they take in data, text, vision, audio, multimodal.
Yeah, covering all the senses AI might have. The paper notes the efficiency difference. AI can process data incredibly fast, but humans are still much better at integrating senses seamlessly and understanding context.
And cross-modal models are key here, linking different data types.
Absolutely. Like SegLP for text-image, AudioGen for text-to-audio, models that handle speech-to-text and back, even models combining audio, vision, and language. It's about creating a more holistic understanding.
And safety checks are important here too. Human oversight, content filtering.
Essential, especially with perception, making sure the inputs are safe and the outputs are appropriate.
Okay, last core component. Action systems. How agents actually do things.
Right. Interacting with the environment. The paper clarifies terms like LLMs, LMMs, large multimodal models, RFMs, robotic foundation models, LAMs, language agent models, basically different flavors depending on what they interact with and how.
And they learn actions through in-context learning, supervised training, reinforcement learning.
All of the above, learning from examples, explicit training, or trial and error with rewards. A big focus now is also on tool use.
Agents using external tools to get things done, like calculators, search engines, scientific software.
Exactly. From specific scientific tools like ChemCro to general-purpose ones, the agent needs to learn when and how to use these tools effectively. It dramatically expands what they can do.
Wow, okay. That's a really comprehensive look at the building blocks. It feels like we've dissected the agent's brain and body.
That's the idea behind the paper structure, yeah.
So the next big part is self-evolution. How these agents can get better on their own. This sounds like where it gets really advanced.
It is. Moving from static systems to ones that can autonomously improve and adapt. It's inspired partly by AutoML, automated machine learning, where the system optimizes itself.
Right, instead of humans tweaking everything, the AI learns to tweak itself.
Kind of. The benefits are potentially huge. Better performance, less manual effort, maybe more like how natural intelligence develops.
How do they optimize themselves? Trial and error.
That's one way, using evaluation signals. Try something, see if it works better, keep it if it does, like evolution. Or using more direct optimization signals where the system gets gradient-based feedback on how to improve, like with OPRO or TextGrad mentioned in the paper.
And they need metrics to know if they're improving, right? Performance, efficiency.
Exactly. Accuracy, speed, resource use, but also qualitative things like fairness or consistency.
The paper also talks about optimizing the workflow, how the different parts of the agent work together.
Yeah, agentic workflows. If an agent uses multiple LLMs or modules, optimizing the connections and communication between them, the edges in the workflow is key for complex tasks, representing these workflows as graphs, neural nets, or even code.
And tool use comes up again in self-evolution, learning to use tools better or even making new ones.
Absolutely. Deciding if a tool is needed, planning the sequence of tools for a task, these are skills the agent can learn and refine. And yeah, even creating new tools on the fly if needed, like with systems called toolmakers or Creator.
That's pretty meta, creating its own tools.
It is. It's a significant step towards more autonomous capability.
And this self-improvement can happen online, offline, or hybrid.
Right. Learning continuously from live interactions or from batches of data offline or a mix. The paper also mentions dynamic parameter tuning, adjusting internal settings automatically, and this core idea of knowledge expansion.
That intelligence grows as knowledge grows.
Kind of, yeah. The paper frames intelligence, ICAGENT, as potentially a non-decreasing function of knowledge. Expanding the world model is key to this growth, and a really exciting application is autonomous science.
AI designing and running experiments.
Pretty much. Systems like AI Scientist or Camosis 2.0 are examples where agents generate hypotheses, plan experiments, use tools, and analyze results, accelerating discovery. Though LLMs still struggle with some quantitative stuff without tools.
Okay, so individual agents can evolve. What about groups of agents? That's the next section, right? Multi-agent system.
Exactly. Collective intelligence. Moving beyond one agent to how multiple agents interact, cooperate, maybe even compete, inspired by nature, like ant colonies or human societies. The wisdom of crowds idea.
So what are the key things for LLM-based multi-agent systems? Communication.
Communication is fundamental. How do they talk to each other? What protocols do they use? Agent bench is mentioned as an interface example. Collaboration is another, shared goals, norms. And composition, are the agents all the same, or heterogeneous with different skills?
Getting the communication right sounds critical. Standard interfaces, protocols.
Definitely. The paper discusses next-gen protocols needing things like identity management, negotiation capabilities, flexibility, how agents know who they're talking to and can agree on tasks.
And how these systems are structured matters too. The topology.
Hmm.
Centralized versus decentralized.
Yeah. Static structure or dynamic. One leader agent or distributed control. Hybrid models often make sense, balancing coordination and autonomy, especially as systems scale up.
What kinds of interactions happen between agents?
All sorts. Consensus building, like the reconcile system. Collaborative learning, sharing experiences, learning from peers, even observational learning. And teaching or mentoring between
So
agents.
they can actually teach each other.
That's the idea. Passing on skills and knowledge within the system. All this aims towards emergent collective intelligence.
Where the group is smarter than the sum of its parts.
Precisely. New capabilities emerge from the interactions beyond what any single agent could do. It's a dynamic process.
And evaluating these systems means looking beyond individual performance.
For sure. You need to measure interagent dynamics, collaboration efficiency, overall task success, decision quality, both cooperation and competition aspects. Benchmarks like master on reasoning tasks are mentioned.
Okay, this leads us to the final and maybe most important part, safety. Building safe and beneficial AI agents.
Absolutely critical. The paper splits threats into intrinsic vulnerabilities within the agent and extrinsic risks from interactions with the world or other agents.
Intrinsic threats to the LLM brain include jailbreaking, prompt injection,
Yeah. Jailbreaking is tricking the model to bypass safety rules. Prompt injection is sneaking in malicious instructions. Data poisoning is corrupting the training data to create backdoors. These target the core model.
and other parts can be vulnerable too. Perception, action.
Right. Perception systems can face adversarial attacks inputs designed to fool them. Action systems might have vulnerabilities in how they use tools, or even supply chain attacks on the tools themselves.
Then extrinsic threats, manipulation through memory, harming the environment, bad interactions between agents.
All potential risks. Messing with an agent's memory, agents causing physical or digital harm, agents acting maliciously towards each other. Privacy is also a concern, attacks trying to infer training data or extract sensitive info.
The paper also mentions superalignment. That sounds like alignment plus plus goal.
Kind of. It's about ensuring alignment for highly capable, potentially super intelligent AI, especially on long-term complex goals. Going beyond current techniques like RLHF to ensure future advanced AI remains beneficial.
And finally, this idea of a safety scaling law. As capability goes up, risk might too.
That's the concern. More powerful agents might pose greater risks if not developed carefully. It highlights the constant trade-off and the need to prioritize safety alongside capability development.
Wow. We've covered a huge amount of ground. From the basic building blocks inspired by the brain, to how these agents learn and evolve, how they might collaborate, and the absolute necessity of building them safely.
It really is a comprehensive overview. The paper lays out the landscape, the incredible potential, but also the significant challenges we need to address to get this right.
It definitely leaves you with a lot to consider about where this technology is heading. That interplay between capability and safety feels like the central question, doesn't it? How do we unlock the benefits while managing the risks? Something for all of us to keep thinking about. Thanks for diving deep with us today.